When a common ion is present in a solution, the potency of an acid or base can be reduced. In this example, we will have sodium fluoride, which will dissociate into sodium and fluoride ions, as well as hydrogen fluoride, which will dissociate into hydrogen and fluoride ions. Notice how fluoride is present in both dissociations and thus is the common ion. For example, if we have an arbitrary amount of sodium fluoride in the solution, we will notice that it will dissociate into some sodium ions and some fluoride ions. Similarly, hydrogen fluoride will do the same. However, since we are in a solution with fluoride ions already present, the equilibrium will be pushed to the left. Remember that hydrogen fluoride must dissociate since there are no hydrogen ions present initially. However, due to the already high presence of fluoride ions in the solution, the amount that dissociates will be marginal, thus reducing the amount of hydrogen ions present. Let's say we have a polyprotic acid, in this case the triprotic acid, phosphoric acid. Phosphoric acid will dissociate into its aqueous parts, dihydrogen phosphate and a hydrogen ion. This dihydrogen phosphate will further dissociate into another hydrogen ion and hydrogen phosphate. However, if you notice that there are already hydrogen ions present from the original phosphoric acid dissociation, you could see that dihydrogen phosphate will only dissociate further due to the lack of initial hydrogen phosphate. This trend will carry down the chain, continuously decreasing the amount of hydrogen ions released. Buffered solutions are solutions that can resist changes in pH. This can be accomplished by adding a weak acid or base with its respective salt. This is just the basics of buffers, and this idea will be further expanded throughout the video. Before we begin answering the question, we will require two equations. The first equation will be the equilibrium constant for the dissociation of a monoprotic acid labeled HA. We will modify this equation by isolating the concentration of hydrogen ions. In this state, it becomes apparent that the concentration of hydrogen ions varies directly to the ratio of HA over the conjugate base. This is because the equilibrium constant is by its name a constant and unchanging. Thus, the only change that can modify the concentration of hydrogen ions is the change in the ratio. This will be more important later, but for now we can put it to the side. The second equation we will need is the interaction between HA and a strong base such as hydroxide. Since hydroxide is such a strong base, we can assume that the reaction goes to completion rather than an equilibrium. If we set up an icebox for the equation, we can be general and say that our initial HA concentration is the concentration of HA. We'll repeat this for the rest of the species. Before we continue to the change portion of this icebox, I should make it clear that the concentration of HA in this solution is greater than the concentration of hydroxide, with hydroxide acting as the limiting reactant. If we do the stoichiometry, both reactants will decrease by the concentration of hydroxide, and both products will increase with the concentration of hydroxide. By completing the icebox, you will notice that HA has reduced by the concentration of hydroxide, and the conjugate base has increased by the concentration of hydroxide. These are the two species we care about, so the rest can be largely ignored for now. Now regrouping what we have, on the left side is the change to HA and A- after the addition of hydroxide, and on the right side we have our first equation derived from the dissociation of HA. When we combine both ideas, we get the resulting formula. Notice how the ratio is what decides the hydrogen ion concentration, which thus must change pH. So we'll disregard the rest and focus on the ratio that we made. Now remember, we want this ratio to be reasonably close to the original HA over A- ratio. So if we say, for the first example, that we have 1 molarity of HA and 1 molarity of A-, and we add a small amount of 0.5 molarity hydroxide and calculate it out, we end up getting a ratio of 0.905, which is reasonably close to the original of 1. On the other hand, if we add something more drastic, such as 0.20 molarity hydroxide into the equation and calculate it out, we get a number around 0.667, which is much further away from the original of 1. In order to derive the Henderson-Hasselbalch equation, we will first require our modified equilibrium constant expression that we arrived to from the dissociation of the monoprotic acid HA. If we take the log of both sides, simplify the log, and multiply both sides by a -1, we get this equation. Some of you may notice ways to further simplify this equation down, but to help you out, I will provide some abbreviations in the top left corner. Taking these into account, we reach our final equation. Similar to the origin of this equation, the ratio is still the main factor that decides pH, as pKa is still a constant and can't modify itself to change pH. Imagine the following situation, where pKa is equal to pH. By setting the equation as such and solving it out, we eventually come to the conclusion that the ratio between HA and A- should be 1. But why? Why should the ratio between HA and A- be 1? The answer is because when the ratio is close to 1, it will change the least, when in this case, hydroxide is added. Let's set up two examples. On the left side, the ratio is equal to 1, and on the right side, the ratio is equal to 100. Let's add a small amount of hydroxide, around 0.01 molarity, and come to the end result of approximately 0.980, which is reasonably close to 1. On the right side, however, when we add 0.01 molarity of hydroxide, the ratio comes out to 49.5, which is much further away from 100. So in conclusion, because we want our ratio to be as close as it can be to 1, we require that pKa is as close to the pH that we require. In order to understand what a millimole is, we should first see the graph of a titration. I'll mark the equivalence point here for you, and you can notice how steep the curve gets. Even adding a small amount, as shown here, can increase the pH substantially. Thus, in order to have very precise measurements, we must use smaller quantities. We achieve this through the millimole. While the millimole is a small measurement, it can't be used with molarity without a few changes. Molarity is equal to mole over liters. That can't change, but we can make a few equivalent fractions. If we multiply both top and bottom by 10 to the -3, which is a valid math move, we could substitute millimole for the numerator and milliliter for the denominator and still have a way to use molarity. If we take another look at our titration graph, you will notice that at any point beneath the equivalence point, there are more hydrogen ions than hydroxide ions. At the equivalence point, there is an equal amount of both, and at any point above the equivalence point, there are more hydroxide ions than hydrogen ions. Since the equivalence point is where there is an equal balance, any addition of a strong base that dissociates into hydroxide will immediately turn the solution basic, similar to if you were adding a strong base to water. Let's say we have a weak acid, such as acetic acid, and we add enough hydroxide to neutralize it. Remember that hydroxide is a strong base, so we can think of it as a stoichiometry rather than an equilibrium. Since we have the same amount of acetic acid as hydroxide, in theory we should only be left with acetate and water. Now remember that since acetic acid is a weak acid, its conjugate base must be a relatively strong base. This strong base will react with the water in order to regenerate acetic acid and hydroxide. We can set up an icebox to calculate the pH. In this situation, let's say we have 0.050 molarity of acetate and some concentration of water. Since water is a pure substance, it won't be used in the equilibrium constant expression, so it can relatively be ignored. Now, remember that we've neutralized all the acetic acid, and so we have none initially, and essentially no hydroxide either. Since we have no acetic acid, the equilibrium must go right. The reactants will decrease by some number x, and the products will increase by some number x. The constant for this reaction is 5.6 times 10 to the negative 10, which is really small, so we can assume that the change to the reactants is negligible. Plugging the numbers into the equation, we can solve for x, which is also equal to the concentration of hydroxide. Using this information, we can calculate the pH, which you'll notice is greater than 7. Similar to the last example, let's say we have a weak base, like ammonia, and a strong acid, like hydrogen ions, which form ammonium. Again, since the hydrogen ion is a strong acid, we can think of this as a stoichiometry rather than an equilibrium. Since we want this to go to equivalence, we should have the same amount of both reactants. After the completion of the reaction, we are left with only ammonium, which is the conjugate acid from a weak base, meaning it acts as a strong acid, thus dissociating into ammonia and hydrogen ions again. The increase in hydrogen ions decreases the pH from 7. An acid-base indicator is a molecule that changes color depending on the pH of the solution it is present in. The video here shows phenolphthalein, which changes color as sodium hydroxide is added to make the solution more basic. Going back to our titration graph, let's label our equivalence point. We want our acid-base indicator to capture the equivalence point. For example, if we use phenolphthalein, you will notice that it does not capture the equivalence point. Similarly, bromphenol blue will not capture the equivalence point either. However, bromthianol blue will capture our equivalence point. When choosing an indicator, make sure it captures your equivalence point.